So we're asked to use the ratio test to determine the radius of convergence. So the ratio test is limit as n goes to infinity for the a sub n plus 1 term divided by the a sub n term, and that's the absolute value of that limit. So we could start off with the n plus 1th term. This is 2 parentheses n plus 1 factorial over n plus 1 to the 2n plus 1 power, and then that's times x to the n plus 1. I'm going to put that in the numerator though. Like if you're multiplying by x to the n, that's x to the n. Well, if you're multiplying by x to the n plus 1, you can just move it upstairs because it's got a little 1 underneath it. That way, I'm dividing this a sub n term. And when I do that, that means I'm going to have to flip and multiply at some point, right? So that way, if my x to the n plus 1 is already in the top, then I can see something cancel out. So I'm flipping and multiplying. So everything I'm thinking about over in the bottom is now going to be on the top. And then this, vice versa. This is 2 parentheses n plus 1 factorial, and then it's x to the n plus 1. Oh, no. Wow. No, that's just repeating what I just did. Sorry, this is the a sub n term. So this should just be n to the 2n over 2n factorial x to the nth. I just started doing the a plus 1th term, but we're supposed to be dividing by the a sub n term. So I flipped this. That way I could multiply the two fractions together after dividing. Okay, so there's some things that are going to cancel out, some things that are not. So here inside this factorial, this is like 2n plus 2, right? Because you can distribute the 2 to everything on the inside. So this is 2n plus 2 factorial. So that means we've got 2n plus 2 times 2n plus 1 times 2n factorial. Because the factorial is multiplying all those descending integers. Okay, n plus 1, and then if we distribute that, 2n plus 2, and we're multiplying this by n to the 2n power, and then this is 2n factorial. Oh, I dropped my x to the n plus 1 because I have x to the nth here. So x to the n plus 1 divided by x to the n, those powers can subtract to give us just x to the first power. And then I also expanded this factorial so that the 2n factorials can cancel. So we've got 2n plus 2, 2n plus 1, n to the 2n power over n plus 1 to the 2n plus 2. Let's see. So we're still evaluating the limit as n goes to infinity. I just dropped that notation to save my hand some writing, I guess. But when you do the ratio test, you're valuing the limit as n goes to infinity. Let me see what else we can do here. 2n plus 2. Okay, I think I know where to go next, but this is something that we should probably review real quick because it comes back in Calculus 1. When we were looking at what's usually looked at in Calculus 1 is the limit as n goes to infinity of the compound interest formula. Looks like this, right? Because with the compound interest formula, you're dividing, if you compound every day, then n equals 365. If you compound every month, then n equals 12, okay? And now if you compound an infinite amount of times per year, if you forget about compounding by some certain pay period or by some certain date interval, if you want to compound an infinite amount of times per year, then that's a calculus problem. It's the limit as n goes to infinity. And if you remember, that's where we get the special number e from. E was first derived from that compounding continuously formula. I'm pretty sure that's where it first came from. My math history is actually not my strongest part of my mathematics. But another way to look at this inside, this is n plus 1 over n to the nth power. And that's what we actually almost have over here. We're taking a limit as n goes to infinity. Now this is x times 2n plus 2 times 2n plus 1 times n to the 2nth over, now down here, this is the same as n plus 1 to the second times n plus 1 to the 2nth power. Okay, so check to see where I got that from, right? This is still the same as this, because if you multiply two numbers with the same base, the powers add. So that'd be 2 plus 2n, which is the same thing that we have over here. And the reason why I did that is because now we can start trying to evaluate this crazy limit that's going on over here. This is the limit as n goes to infinity of x times, if you were to expand all this, that'd be 4n plus 2n plus 4n, that makes plus 6n. Sorry, this is 4n squared plus 6n plus 2. And if you were to expand this down bottom, that would be n squared plus 2n plus 1. We'll need to look at that in just a second, but the whole point of rewriting this is now this is n over n plus 1, all being raised to the 2n power. Right, because if you were to put this 2n power back on top, this would be n to the 2nth, like we have up here, and this would be n plus 1 to the 2nth over here. And now we can use our properties of limits. We can evaluate this limit separately from this limit. Okay. Can I move this easily? No. Okay, so let me take a quick picture. Okay, so this is evaluating this limit over here. The limit as n goes to infinity. Look, the powers are the same. We got n to the second over n to the second. So that means it's going to be a ratio of the leading coefficients for this limit. You got a 4 up top and a 1 on bottom. So this is going to be 4x for this limit. Okay, and so you'll just want to go back and check. That's like when you find horizontal asymptotes previously in math. If the powers are the same, then it levels off over time as a ratio of the leading coefficients. And then here, evaluating this limit, this is actually just a flip of, let me see. I actually got to look at it again. Limit as n goes to infinity. The compounding formula is 1 plus 1 over n, where this would be usually where your interest rate goes, but we just use 1 for 100% for simplicity. So that's the same as this is n over n, so this is n plus 1. Okay, so we actually have a flip of the compounding continuous formula. This limit as n goes to infinity of n over n plus 1, that's 1 over e. Okay, because from what we know previously in math, this is e. The limit as n goes to infinity of 1 plus 1 over n to the nth power. We've let that be the exponential constant e, which is the same as n plus 1 over n. We have the reciprocal, so we have to use 1 over e over here. Okay, and now we're done the calculus stuff. The limit has been reached. We reached the limit as n goes to infinity. Pretty tough problem there, especially this little piece. That's not something that's usually on the tip of a calculus student's tongue, but right. So the absolute value of this limit is supposed to be less than 1. So if you solve for x, x is going to be less than e over 4. And then x has got to be greater than negative e over 4 because it's an absolute value. So if you're looking for the radius, like this problem is talking about, your interval is e over 4, negative e over 4 to e over 4. And the radius is just the distance from one endpoint to the center. So the radius is e over 4.